All right. So your second exam's on Monday. Class is 9, and then 11. Class 10 was our first exam, and then 11 through Wednesday, which was the second day of inverses. Today we're going to start quadratic functions. This will not be on your test, and the homework for this will be due next Wednesday, which is 4-2. Progress reports are due today, which was news to me. I did write to the registrar and ask permission to try to wait until after Monday's test so that, you know, we'd have a better picture of where you are. And depending on her answer, I'll either have to do them today and send them in. That's sort of like your midterm grade at this point. Or she'll say, sure, you can wait to Monday's exam and get them in on Tuesday or Wednesday. So you'll either be seeing, I think they only send you the report if you're in danger of not passing the class. Okay, so let's start today. If I get this in the right order, we can start. Okay. So quadratic function. We should be familiar with the form of a quadratic because we spent a class, right, learning how to solve different types of quadratic equations using different methods. And we all remember that we can always solve a quadratic equation using the quadratic formula when it's set equal to 0. So that was learning how to solve specific types of equations. Now we're going to learn how to graph quadratic functions, which when they're in their polynomial form, now I just used a word, you may or may not know polynomial form is this form right here where you have 3 terms. When you have adding and subtracting, the individual parts are called terms. So this is in polynomial form, which is what you're used to seeing. And the only specifications on this, other than the fact that A, B, and C have to be real numbers, is that A cannot equal 0. Why do you think we say A can't be 0? Why do you think we have to say that in order for this to be a quadratic function, A can't be 0? Yeah, then it's just linear. If A is 0, this whole first term just gets wiped off the map, which I can do pretty quickly, boom, and then that's no longer a quadratic. That's a linear function. So this is what we call the polynomial form. And that's because you have this addition here. It could also be subtraction if B or C is negative. And just a little, if you want a little language, we call this first term the quadratic term because it has your square. Call that the quadratic term. We call this the linear term because it's x to the first power. And again, as Cooper said, if A was 0, then it would be a straight line. And C is the constant term. Your eyes all set today? Good. Much better? Did you listen to the video? Good. All right. We call the graph of a quadratic function a parabola. Okay, so we've worked with these with our transformation, all those transformation classes we had, we were working with transformations of your parent function f of x equals x squared. So let's do some work with this today. So we just saw the parent of all quadratic functions is f of x equals x squared. Okay, here it is right here, f of x equals x squared. The point 0, 0, right down here, we call the vertex. Because if you notice, this function from negative infinity to 0 is decreasing. And then at the point x equals 0, it turns itself around and starts increasing. So that's a very pivotal point, so to speak, the vertex, right? You change from being a decreasing function, in this case, from a decreasing function to an increasing. Okay, and we know that this continues to increase forever and ever and ever. So let's graph the function. Let's do a transformation of our parent function. And this is going to be our new function. G of x equals 2 times x, the quantity x minus 1 squared, take away 3. So let's play the game we played when we were doing transformation of functions. Let's pick a couple of key points on our original function. We'll pick a couple of key points, and then we'll transform them. So let's pick a couple on to the left of 0, and then let's pick a couple of points to the right of 0. So want to give me some points? Any old points that you're familiar with? A lot of you are already writing them down. So a couple of key points on f of x equals x squared. 1, 1, okay. 1, 1. 2, 4, okay. So we're done with the positive side to the right of 0. How about, well, I'll put in 0, 0. Negative 3, 9, and one other. Negative 1, 1. Okay. So let's use our transformations here. Well, our knowledge of transformations. This will be a nice little review to determine where these points are going to be. Are going to move, right? They're going to be moved, and their shape's going to change. The shape of the parabola is going to change. So first of all, someone want to tell me all 3 transformations that must happen verbally from looking at the new equation? You want to see how set you are for Monday by telling me all 3 transformations? Anybody feeling brave? William?
To the right.
Okay, so we're going to move right 1 unit. That's one transformation. Let's just stop right there. So let's move right 1 unit. We got negative 3, 9, negative 1, 1, 0, 0, 1, 1, and 2, 4. So let's move right 1 unit, which is going to change our x value. So that means add 1 to all x's. Okay, so let's do that. Let's add 1 to all my x's. Okay. Negative 2, 9. Help me. 0, 1. 1, 0. 2, 1. And 3, 4. Okay, William's all done. That's my first transformation. Another one? Move down 3, right. Move down. Oh, wait a minute. I'm doing all these transformations. What should I be doing first before I start my movements? I should always change my shape first. So we're not going to do that yet. Let's talk about our 3 transformations, which was my original question. We move down 3 units. So we subtract y, 3 from y values, from all the y's. And then what's our last transformation? Okay. Are we outside of our square or inside of it? Out. Right. It stretches vertically, right. Vertical, stretch, and anytime we're stretching or shrinking is when we use the word factor by a factor of 2, right. So that means we're going to multiply all our y values by 2. Multiply all y's by 2. Okay. Yes, it would be horizontal if it was inside. And if that 2 is inside, we'd be shrinking by a half. Okay, so let's start this process again. So we have negative 3, 9, we have negative 1, 1, we have 0, 0, 1, 1, and 2, 4. Okay, all of my shape changing has to occur first. And the only shape changing we're doing is we're stretching this thing vertically by a factor of 2. So that means all my y values get multiplied by 2. All my y values get multiplied by 2. So we get negative 318. All my x values stay exactly the same. So we got 2, 0, 2, 8. Did I do that correctly? Everybody agree with that? All right, then we can start our movements up and down or right and left. And it doesn't matter which way we do it. All right, so I don't know if you have a favorite. Let's do our movement down. Let's subtract 3 from all the y values. So now we have negative 315, -1, -1, 0, -3, 1, -1, and 2, 5. Did I do my subtractions right? People agreeing with me out there in student land? CJ, you agreeing so far? Okay, thank you. And then finally, we have to move right 1 unit, so that means I add 1 to my x's. So I get -215, 0, -1, 1, -3, 2, -1, and 3, 5. Okay. Whew. So these will be the new points that I graph. So instead of -39, I'm -215. So -2 is, let's see, where is that -2? I can't see it. I'm going to 0, -1 is right here. 1, -3 is right here. 2, -1 is right here. 3, 5 is right here. And I would also have had what other point? If I had done -29, I mean -24, but where would it have ended up? It would have had to end up where? So if I do -215, I'm going to be up here somewhere. Let's see. I'll just put that in then. -215. So let's draw this transform graph. Okay. So it's skinnier than the original graph. That's because it got stretched. It grew really quickly like you all did at adolescence. At least usually boys grow pretty quickly at adolescence. And it moved. The vertex moved from 0, 0 to where? Where's our new vertex? See, here's where the vertex started, right here at 0, 0. How did it move? Where did it move to? What point? Right here, right, 1, -3. So a new vertex is 1, -3. Because notice the stretch didn't affect it at all, right? Because anytime you multiply 0 by any number, it's still going to stay 0. So it's really just your horizontal and vertical ups and downs and rights and lefts. So we moved right 1, so we went from 0 to 1. And then down 3, we went from the y value 0 down to -3. So the vertex of my parent function ended up becoming 1, -3. So now notice, given that this was our original equation for this function, notice that this isn't in our polynomial form. It doesn't say 2x squared plus something times x plus a constant. It's a new form. Can you look at this and see where the vertex is? From looking at this equation, can you see where the vertex is of our new transformed parabola, function g? Can you see it in that equation? Yeah, right? That's pretty cool. If your function's in this form, you're going to be able to look at it and get a key point right away. You're going to be able to get the vertex. So here's your vertex 1. Here's your x value of your vertex. And here's your y value of your vertex, -3. You get it right away from looking at this form. So this is going to be a particularly useful form for us if we have to graph a parabola that's been transformed from our parent function x squared. We know immediately where the turning point is. Now the name for the vertex is a turning point. Okay, vertex is the, mathematical term. Yeah, when you square x minus 1, if we wrote, let's put this in, let's take it from this form, which we're going to be calling in a minute the standard form. We're going to be calling this the standard form in 1 second. Let's put it into polynomial form. where it looks like ax squared plus bx plus c. So let's put it in polynomial form to try to answer Gina's question. Okay, so what would be the first thing I would do to the right side here if I wanted to start to transform it into polynomial form? I got to square x minus 1, right? So 2 stays out here, and I'm going to multiply it by something, and the minus 3 stays out here. So how do I square x minus 1? X minus 1 squared, what's that going to give me? Table 2, I know you like working ahead, but it would be helpful if once in a while you help participate to help us out. Anybody? X minus 1 quantity square? Seth or CJ? How do I square x minus 1? Jonah? No, I want to square it. I don't want to undo it. Okay. X minus 1 times x minus 1, and what's that give us? X squared minus 2x plus 1. Okay, so that's what goes in here, x squared minus 2x plus 1. Now I double it all, right? Double it all, and then subtract 3. So my final equation is, get rid of this. Woo, I don't want that big circle. So my final equation is 2x squared minus 4x minus 1. So these are exactly the same equations. They're just different forms. Now, the only bit of information that's the same in both of them, if you look at this first form and the second form, what's the only part that's exactly the same? Seth? A, right? A's right here out front. It's 2. A is the coefficient of your x squared term. It's 2. So A is the only one that stays the same. The minus 1 here is just like the constant term with a quadratic function acts the same way as with your linear function. Your constant term is your y-intercept. Here's your y-intercept, 0, negative 1. Because when x is 0, all that disappears, and there's your y value, negative 1. So there's some relationship to like your linear functions. Okay, so we call this the standard form. We call this the polynomial form. And your work in this section will have you going from one form to the other. One form gives you different information than the other. And you're going to learn how to go from one form to the other. We just went from the standard form to the polynomial form. In a few minutes, we're going to learn how to go from the polynomial form back to the standard form. Okay. You know, it's kind of hard when you change books because in my mind, I always used to call this the standard form, and I would call this the vertex form since I can see the vertex right away. But our book happens to call this the standard form, and I don't really know what they refer to that as. Oh, wait a minute. Maybe that was my old book. Quadratic function form. Nope, they didn't give that a name. Okay. All right, so let's move along. The standard form of a quadratic function is given by this form, which you can immediately see the coordinates of your vertex. Notice it's a times the quantity x take away h, quantity squared plus k. So when k is a positive number, you're shifting your parabola up. When k is a negative number, you're shifting it down. When h is a positive number, you got x minus h, you're shifting it to the right. And when h is negative, that would make that x plus h, you're shifting it left. Okay, so notice this form has a subtraction inside the parentheses and an addition outside the parentheses. So what transformations have happened to our original function? Okay, I think we just covered that. We move vertically k units. We go up if k is greater than 0, and we go down if k is less than 0. right? Help me out with the inside part, the H part. See if we can talk about that transformation. Put that in green. So here's our K. Oops, blue. Now we'll talk about the transformation that happens here. So what's that transformation? Well, we don't know yet whether it's right or left because we don't know the value of H. Back. Okay, hang on. So back here we could say, where are we? Right here. We could say here we go to the right because we know the number. We know the value of H is 1. Yeah, so no, it doesn't say here whether H is positive or negative. It just says take away H. So you've got two cases here where H is positive and where H is negative. So what kind of movement is it if you're inside here and you're subtracting H? Yeah. If H is bigger than 0, then we look at something like this, x minus 1. And how did that move? Did it go left or right? Right. Okay. So if H is a positive number like x minus 2, x minus 3, it goes to the, if H is positive, it would look something like this. Here's the value of H. H is 4 because that subtraction sign is already there. So that tells you you move right. Okay, so you're going to move right if H is positive, and you're going to move left because if H is negative, then you're going to have this, subtracting a negative 4. It's no different than what we just did for transformations, except for you're used to seeing x take away or x plus. So if H is negative, we move to the left. If H is positive, we move to the right. So this is a horizontal shift. All we're doing is forget the sign right here. Just look at your number. If H is a positive number, Septov, then you're saying X take away whatever that number is. That's a horizontal shift to the right. I know. Right, right. And if it's minus, that number there is positive. When that number is negative, it becomes your plus, which, yes. Okay, now you okay? All right. All right. Phew. All right. It's tough. This is tough stuff, folks. Okay. Finally, we have to deal with the A. What's the A going to tell us? Cooper? Okay, it's going to be some type of vertical stretch or shrink. Or compression is another word if you want. Compression, shrink, whatever you want to say. So A is going to tell us about whether you have a vertical stretch or shrink. And if A is greater than 0 in absolute value, you have a stretch. And if A is between 0 and 1, you have a shrink by that factor. Okay. So the standard form, what they're calling the standard form right here, is convenient because it immediately identifies the vertex of your parabola. You pluck off H and K. Boom, you're done. Cooper? Yes. Absolute value. Yeah. The standard form is convenient because we immediately get the vertex of the parabola. If A is a positive number, that also tells us about how the parabola opens up. Does anybody know if A is positive, how the parabola opens? Up. It opens upward. It's a happy parabola. So when A is positive, you have a happy parabola. It opens upward. A is negative. When you're feeling negative, you're feeling down, right? The parabola opens downward. Oh, thank you. Yes, it is reversed. 0, 1. Yep. It's amazing what happens when you go too fast, isn't it? That reminds me, I don't want you going too fast on Monday, so get here early to take your test. Come in at 10 o'clock. You have plenty of time. You don't have to hurry yourself. You won't make little mistakes like I just did, okay? Use the fact that you have that 40 minutes unscheduled prior to class starting. That's why we did it that way. All right, so if the absolute value of A is small, the parabola opens more flatly than if it's the absolute value A is large. All that's saying is it's a very wide parabola when you have a fraction for A. And when A is large, the absolute value, we're not dealing with whether it opens up or down. It's being stretched. So it's very narrow compared to when A is a fraction. It opens up much more flatly, or it's wider in scope. Okay, so also, if we were trying to make an accurate sketch of this parabola, we want to find our x and y intercepts, which I think you all know how to do, I hope by now, but if not, we'll review it. So do not fear. All right, so here is a parabola in standard form. Tell me anything you know about this parabola, anything at all, just from looking at the equation. And then we'll put it in the right 1, 2, 3, 4, 5. Anything at all. We know that it moves up 4 units, right? And that's what this thing tells me. So what's happened to my original vertex, Gina, which was originally at 0, 0 for x squared? I know one coordinate right now. What is that? Well, we don't know yet what that one is. We just know that the y value has been shifted up 4. So from 0, my y value being 0, it's moved up 4. So I know that. What else do I know from looking at that? It moves to the right 1, right. So whatever number appears right there after the subtraction sign, that's the x coordinate of your vertex. It moves right 1 unit. This all follows from all the work we did with transformation. So right now, we know where the vertex of this thing is. 1, 4. Cool. That's a really important point to be able to graph right away. All right, what else can you tell me? So Dan's taking a turn and Gina's taking a turn. Austin? It flips, right? It flips over the x-axis, right? It's moving, so that another way to say that is my parabola is opening downward, because what value is -1? What value? What letter do we give to that? What letter do we give to that number out there, -1? A. A is -1. Since A is less than 0, this is going to go downward. All right. We know A is -1. We know H is 1 and K is 4. And we know what the vertex is. Wow. That's a lot of information right away from just looking at that equation that you've been able to gather. How do we find the y-intercept? Anytime we have an equation, how do we find the y-intercept? X equals 0. So find the y value for when x is 0. So let's do that. Let's put 0 into our function. It says the opposite of 0, take away 1 squared plus 4. So the opposite of -1 squared plus 4 is 3. So 0, 3 becomes our y-intercept. Right away, you can get another point without any work, because you know that any parabola is going to be symmetric around its vertex. Now, we were working with the y-axis being the symmetrical axis with x squared. Now, notice where your vertex is. It's at 1, 4. So that means the vertical line that goes right down the middle of this parabola goes right through your vertex. That line has the equation x equals 1, because every point along there has an x value of 1. So that means that the left side of this parabola can be folded along that line and have a matching point on the opposite side. So notice I just plotted the point 0, 3. 0 is only 1 unit to the left of 1. So that means 1 unit of movement to the right, I'm at exactly the same height. So I can automatically get another point for free, 1, 3. It's just on the other side, that line of symmetry. So every time you plot your y-intercept, just go in the opposite direction, whatever that direction may be. In this case, it's to the right of your vertex, the same number of units, and you're at exactly the same y value. That's the symmetry aspect of a parabola. So we've got 3 points already on this parabola that we just graphed from knowing the vertex and the y-intercept. Now we have to find the x-intercepts, and that's why we study how to solve quadratic equations, because the x-intercept are the zeros of your function, same thing. X-intercepts are zeros of the function. They both mean the same. Is where you set your function equal to 0 or your y value is equal to 0 and figure out what x is. So that's setting a quadratic equation equal to 0 and solving. So let's solve this quadratic equation. There's 2 ways, well, there's 3 ways to do it. I'll see which way you lead me, what path you lead me down here. Okay, so anybody want to help me solve this? How would you approach this if I left you on your own to do this? What would you do? A lot of you are working furiously away here. Want to tell me what you're doing? You got it all done, right, CJ? You got it all done? Brittany, how would you start this if you wanted to solve for x? It is actually already factored because it's x minus 1 times x minus 1. Yeah, okay, so you got to get it into your polynomial form to do that. So Brittany wants to put it in polynomial form so she can use her quadratic equation or factor. So in order to do that, we've got to square the x minus 1, which we've done before. So that's x squared minus 2x plus 1. We just did that a minute ago. But now everything's just being multiplied by -1, which changes all the signs. Okay. And now we have 0 equals negative x squared plus 2x plus 3. All right. Let me just show, do I want to show you this? All right. So Brittany said from here, I'm going to show you 3 ways. She said from here, she would use her quadratic formula, right? A equals -1, B equals 2, and C equals 3. And that's how she'll get the values of her x-intercepts. So x equals -b plus or minus the square root of b squared minus 4ac all over 2a. All right. So x equals -2 plus or minus the square root of 16 all over -2. -2 plus or minus 4 all over -2. So what do we get? X equals -2 plus 4 over 2, and x equals -2 minus 4 over -2. So we get 2 over -2, we get -1. So -1, 0, there's one x-intercept. -1, 0, which I'm having a lot of trouble seeing on this graph. I don't know if it's this first line or because oh, I just see the -2 looks like everything's bumped over. I see -2, 1, there we go. Excuse me, -1, 0. And what's the other x-intercept? -6 over -2 is a 3. Yep. And again, those have to be symmetrical, right? This point at -1 is 2 units to the left of my line of symmetry. So I know my other x-intercept has to be 2 units to the right. It all makes sense. Everything is symmetrical. I have everything I need now to get an accurate sketch of this parabola. I just connect everything. There we go. All right, I don't know if you all want to go through the polynomial form. That's what we just did. We solved that equation. Yeah. What do you want me to do? What would be your first step, Chris? Okay, so you don't want to square everything out. You just want to subtract 4 from both sides. Okay, we can do that. Okay, divide by -1 on both sides. That's fine. 4 equals x minus 2 squared. And this is where I do my grumpy face. Because this is where you're going to maybe run into problems unless you're really, really like got all your algebra antennas up. Okay. How many x-intercepts are we going to have with this parabola before you even get there? You know this parabola opens downward. How many times is it going to cross the x-axis? Twice. We just saw it crosses at -1 and 3. It crosses the x-axis. So that's where you got to be really careful if you use this method. Because what happened in my first class is someone said, take the square root of both sides, which is where Chris is going, but it's plus or minus the square root of 4. That's what you got to remember. And that little grumpy face that you're going to have if you do it that, if you forget that, but if you remember it, will turn into a happy face. Okay? So when you square root both sides, remember you got positive and negative square root of 4. And why is that, folks? The part you never want to remember or like sort of believe is when you write this symbol, we're going to go back. I got to tell you mathematically, I'm obligated. When you write this symbol, it only asks for the positive square root. Wait a minute, Linda, you just told me there's 2 answers. I'm getting there. This really says 2. But the square root of whatever's down here being squared, the answer is not x minus 1. It's, you have to go back a long way. It's the absolute value of x minus 1. Now this is an equation you would have seen from class 9, an absolute value equation. That's the part of class 9 that's going to be on your test Monday is absolute value equations. And do you remember how to solve these? This comes out and gives you 2 different equations. What are they? X minus 1 equals what? And x minus 1 equals what? Minus 2 and plus 2. So x equals -1. There's your first x-intercept. X equals 3. There's your second. So you can always shortcut. You can always shortcut a polynomial, whether it's a simple x in there or an expression, by saying it's whatever is in that parenthesis plus or minus the square root of that constant. But you got to remember the plus and minus, or you're only going to get 1 x-intercept. Now, not all parabolas have 2 x-intercepts. In fact, your parent parabola, x squared, just has, x squared just has 1 x-intercept, the vertex itself. But in this case, when we started to draw this, we knew this would go across that x-axis twice. So that's the only scary part about doing it this way. As Chris says, it's a lot quicker. But Brittany's way is almost foolproof. It takes a lot more work to do the quadratic equation, and you've got to remember it. But you'll get your 2 answers for sure. So here we have plus or minus 2 equals x minus 1. So x equals -1 and x equals 3. Okay, so now the other way I want to show you is taking from, I'm just going to take this equation and bring it over here. I'm going to do what Brittany did, but I'm going to show you hopefully a little quicker for some of us than the quadratic. When we factor, because Brittany mentioned the word factor, we like the number in front of x squared to be positive, right? So it's a -1 right now, which means I have the right, because I'm solving an equation, to divide everything by -1. So I still get 0 here, but now I get x squared minus 2x minus 3. And now I can factor that very easily. I could have factored it over here too, but this is just a lot easier. X plus 3 excuse me, x minus 3, x plus 1. And there are your two x-intercepts. Okay? So there's 3 ways to get the x-intercepts. Depending on what's easier for you, choose one of these methods. Okay? 3 different ways. You can come back and review the video. I'm going to move on. Okay, so let's take a look at what's coming up next, beside all this side note stuff here. All right. So we just did this. We just changed this to the form, the polynomial form, when Brittany had us go through this motion. And what was it down here? Negative x squared plus 2x plus 3. So we've already done this. This is f of x equals negative x squared plus 2x plus 3. Okay? And we can just say see previous problem. Because Brittany already did that for us. All right, so if you're going from this form to this form, you basically expand your polynomial, your binomial here. You expand it by saying x minus 1 times x minus 1, and then combining all your like terms. All right, now the question is, how do we go from the polynomial form to this? This, going from the standard form back to the polynomial, was no problem. We just had to square that binomial and put all our like terms together. But how do we go from this form to here? Well, the good news is that the a in both of these is exactly the same. The a never changes no matter what form you have. So you'll always be able to look at the a and know whether your parabola opens up or down, whether it's a very flat and wide parabola, if a is a fraction, or rather if it's a tall, skinny parabola, if a is a relatively large number. Okay. Now we have to figure out how we go from this form to this form, and we need to find the vertex. Well, the good news, folks, is there's a formula to find the vertex. So if you have your polynomial form, the vertex of the parabola, when it's in the polynomial form, is negative b over 2a is the x coordinate of your vertex, or your h value. So h is equal to negative b over 2a. And k, your output value, is the value you get when you put that back into your function, f of negative b over 2a. So let's just take a look at the one we just did a minute ago. A minute ago, we had this, with Brittany's help, when we put it into our polynomial form. We already know what the vertex of this is, because all we have to do is sneak back here real quick. We know it's 1, 3, so we should get exactly the same answer now. So if it's in this form and we can't look at it and tell, oops, that can't be right. Wait a minute. Because that tells me the x-intercept is, what happened when I expanded this? Oh, it's 1, 4. That's the vertex. I didn't have the vertex listed. Here's the vertex, 1, 4. Okay. See why I knew it couldn't be 3? Because the y-intercept was 3. All right, so we look at this and we say, okay, find the vertex. You say, oh, it's not given to me, so I have to use that formula. So h, which is the value, the x coordinate of your vertex, so that's the x coordinate of your vertex. You can also do that, x with a little sub v, the x coordinate of your vertex, which we're calling h, is negative b divided by 2a. B is 2, so that's negative 2. A is negative 1. So we get negative 2 over negative 2, which is 1. So now I'm halfway home. I have the x coordinate of my vertex, so the value h. Now to get my output y, I have to put the x value into my function. So the y value of my vertex, or k, is f of 1. I just put 1 in, and I figure out now what my y value is. So that's negative 1 plus 2 plus 3, which is 4. Whew, it works, 1, 4. Okay, so when you're given the polynomial form, you can use this formula to find your vertex. Now, does the negative b over 2a remind you of anything? The quadratic formula. And think about where your vertex is. If we go back to the equation we just did, 1, 4 was our vertex. We had roots at -1 and 3. How far apart? How many units are the points -1 and 3? How far apart are they? 4. 4 units apart. What's halfway between -1 and 3? What x value is halfway between? Right? You could go 2 units this way and 2 units that way. You're right at your vertex, right? So think about the quadratic equation. The quadratic equation gives you these two values. The quadratic equation is -b over 2a plus or minus the square root of b squared minus 4ac over 2a. That is your midpoint. The x value of your vertex is the midpoint. It's halfway between your two x-intercepts. So you really don't have to remember a whole new formula because here's the x value of your vertex. It's the first part of your quadratic formula, -b over 2a. And then when you add a number to it, you get this particular x-intercept or root. And if you subtract that, you get this one. So that's really your midpoint between your two x-intercepts. All right, you don't care, but I thought I'd throw it in. All right. So here's something, change the quadratic function to standard form. Okay, or vertex form is just another name for it. Vertex form, I'm going to throw vertex form in there just so it helps you. And then graph the parabola. So you want to do that on your own to see how far you get? And I'll help you out? Or you want to do it together? Let's do it together. Okay, so what's the vertex? How are we going to find the vertex of this parabola? Wake up, yoo-hoo! Are you out there? I know you are. What were you saying, William? Into what? Yes, I have to put it back in, right? I want to put it into that standard form. How am I going to get there? Austin? Find h and k. We've got to find h and k, and how do we do that? Right, the x value of my vertex, so what we're calling h is -b over 2a. So I better identify A, B, and C right from the get-go. So let's come back up here and say what A, B, and C is. So help me with that, Austin. Yeah? Yeah? Okay. So now the opposite of B is -4 over 2 times -1 is 4 over 2, which is 2. Woo, half of it's done. Now how do I get my Y value or my K value? I know X is 2. How do I get my Y value? How do I get my Y value or my K value in this case? Put 2 into the function, solve the function, right? So say f of 2. So that's the opposite of 2 squared. This is where you got to be really careful, folks. Right here. This is not -x quantity square. It's the opposite of whatever x square is. That minus sign goes out front. I was just working with a 1096 student today about that. The opposite of 2 squared plus 4 times 2 plus 1 is -4 plus 8 plus 1, which is 4 plus 1 is 5. So 2, 5 is the vertex. 2, 5. So right away, 2, 5, boing. What's the value of A? It's -1. So that tells me my parabola faces, opens down. Now that I know what A is and I know what H and K is, I can put it into my vertex form. It looks like this. -1 times x take away 2 squared plus 5. Believe it or not, even though you're working with quadratic functions, that's the thing right there that students forget. Students forget to put the square on there. Okay, so don't forget that. You're working with a quadratic. We know it opens downward. The y-intercept, you go back to this form. Go back to your polynomial form right here. When x is 0, what's y going to be? 1. Right here, this tells you your y-intercept is 0, 1. So that has a use. And that's 2 units away from the vertex. So if I go 2 more units, I get another point that's symmetric to the y-intercept. So I have 0, 1, and I have 4, 1, and I have 2, 5. Okay, so wherever that x-intercept is here, it's got to be pretty close to 0. It's going to be a negative number pretty close to 0 when this parabola comes down through. And then this one is going to be 4 point something, it looks like. Okay, so let's take a look at how we find our x-intercept. So our y-intercept is 0, 1. And you put x is 0 in here, out pops 1. All right. Now the x-intercepts. The x-intercepts 0 equals negative 1 times x minus 2 quantity squared plus 5. Okay, I'm not going to use the quadratic formula. I'm going to do it the way Chris did it a minute ago. We're going to subtract 5 from both sides. We could use the quadratic if we want. Divide both sides by negative 1. You get 5 equals x minus 2 quantity square. Let's do it both ways. So 5 equals x minus 2 quantity square. When you take the square roots of both sides, you get plus or minus the square root of 5 here. Yuck! Irrational, so what? Okay, no problem. We're going to estimate it anyway to graph it. Now we drop our parentheses because they're not doing us any good anymore. Boom. And now we solve this for x by adding 2 to both sides. So 2 plus or minus the square root of 5 is equal to x. So those are your two x-intercepts. One is 2 plus the square root of 5, comma 0. And the other is 2 take away the square root of 5, comma 0. If you throw that into your calculator and you get an estimate, so these are the exact solutions to that equation where f of x equals 0. So if we want estimates, I ask you for estimates, say to 2 places, this one would be 4.24, comma 0, and this would be negative 0.24, comma 0. Okay? So you could graph that. If you don't like Chris's way of doing things, then you can do it by doing everything out the long way. Trying to hurry here, see. 0 equals negative 1 times x minus 2 squared plus 5. So Brittany would have us square this. And then multiply everything in the parentheses by negative 1. Then we combine our like terms. And now we use the quadratic. X equals negative b plus or minus the square root of b squared minus 4ac all over 2a. And we got a little bit of simplification to do here. You can see square root of 20 is the square root of 4 times the square root of 5, and it's all over negative 2. So you can see there's a little more work to do it sometimes when you do it with the quadratic. So x equals negative 4 plus or minus 2 square roots of 5 over negative 2. And x equals, there's a 2 all the way around. So you get 2 plus or minus the square root of 5. 2 is a common factor, negative 2 all the way around. So you get the same answer. Some people think that's a little more work. It's up to you. I would probably have divided both sides on that. There's no way you can factor this, so even dividing out the negative 1 here is not going to help you factor it. And how do you know that? Because you have irrational solutions. You can only factor when your answers are nice, rational numbers. So let's throw those points in, and voila, we're all set with, we got a little baby point right there, and we've got a little point right there, and now we can accurately draw a sketch of this parabola. So those are going to be the skills that you need to move between the standard form and the polynomial form. That formula will be helpful to find your vertex. And basically all it is algebraic practice with stuff that you really have been doing all the way along. I don't even know if there's new stuff here today other than seeing the quadratic in this vertex or standard form. All right, so how do we go backwards? How do we go from the graph back to the equation if we're given the graph? So here we have this particular quadratic. We have 3 points. We have our y-intercept at 0, 23. And notice that's 3 units away from our line of symmetry, which goes right down through our vertex. Our line of symmetry is x equals 3. That's our line of symmetry. So we know if we go 3 units from 3 to 0 to the left, we're at the height of 23. So if we go 3 units to the right, we're also at the height of 23. So we have 2 points, 0, 23 and 6, 23. All right, so find the equation of the quadratic function and give both forms, the standard and the polynomial form. So how are we going to do this? Cooper? Yeah? Yeah? You started with this one here, the polynomial, the standard form. Remember, standard is also vertex. So you started with this form right here. And why did you start there? Oops. Oh, that's an H, sorry. The vertex is H. Yeah, so what Cooper's saying is, look, I already know my vertex. Wow, I'm 2/3 of the way there. If you look at this form, this form, you need H, you need K, and you need A. You got 2 out of 3 of those values. You know H is 3 and K is 5. All right, well, that's pretty cool. Wouldn't I get some credit, Linda, if I put that on a test, even if I couldn't find A? Yeah, you'd get some credit. Okay. Well, now what do you need? You need to solve for A. You need to find the value of A. Well, you got a point. You got 2 points that are solutions to that equation. That's what you forget. You forget that these points are solutions. These represent solutions to that equation. Where you see f of x, you can put the number 23. And where you see x, you have a choice. You can either put 0 in or 6 in. Doesn't matter. And solve that equation for A. So pick one of the points. Pick a point from the parabola. Let's pick 0, 23. And let's plug it in and solve for A. Plug in, solve for A. That's it. Just like when you had a straight line and you had your slope and your point. Use your point slope form of a straight line to solve for B. Here we're using our vertex and a point to solve for A. So let's do it. F of x is 23 when x is 0. I know 0, 23 is on this parabola, so if I plug it in, it's a solution, and it's going to help me find A. So 23 equals A. 0 take away 3 is -3. I square it and I add 5. 23 equals 9 times A plus 5. Subtract 5 from both sides. 18 equals 9 times A. A equals 2. I am done. I know A has to be positive because this opens upward. So f of x equals 2 times x minus 3 quantity square plus 5. That's my standard form on my vertex form. And you all can work it out from there. When you work it out to ax squared plus bx plus c, from having this form right here and looking at the picture, do you know any of those values? You have A. Look, here's A. A never changes. If it's 2 in this form, it's 2 in that form. Do you know C? Do you know the y-intercept? Yeah. What's the y-intercept? 23. Now you know C. Well, unfortunately, to find B, you have to do the workout. So you can do that later. I want to move on because we only have 7 minutes left. Well, let's do it really quick. 2 times x squared minus 6x plus 9 plus 5 if I square that binomial. 2x squared minus 12x plus 18 plus 5. 2x squared minus 12x plus 23. So there it is in polynomial form. Okay. A's the same, B's the same as it is on the graph. It's the y-intercept, 23, and B's negative 12. All right, so let's move along here. What key feature of the quadratic marks its minimum or maximum value? What part of your parabola shows the minimum or maximum value of the parabola? The vertex, right? If your parabola opens upward, your vertex is the minimum value. The y value of your vertex is the minimum value. If your parabola opens downward, you have a maximum value. Okay. So we have a couple of word story opportunities where we're having to maximize stuff. So and we only have about 6 minutes left. So I think I'm going to skip this one right here because this is just finding the vertex right here. I'd rather do a story opportunity with you. So here's an arrow. Let's put this into our calculator so we can see it, what it's going to look like. This is, ooh, baby, I really stretched that out. Here's a typical application for a quadratic equation. You're going to be shooting an arrow. It's going to go up, reach the maximum height, and come down. So the question asks, what is the maximum height of the arrow, and how far from its release does it occur? So this is your K value of your vertex, and this is your H value. So H equals negative B over 2A. Let's find that first. B is 2, so we have negative 2. A is negative 0.005, so we have 2 times negative 0.005. We get negative 2 over negative 0.01, which is 2 over 100. So 2 divided by 100 is 100th is the same as 2 times the reciprocal. 2 times 100, which is 200. So that's the maximum, that's the distance, the horizontal distance that this arrow is going to travel before it reaches its maximum height. That's the H value. Now to find the maximum height, we throw 200 back in here into our formula. We say K is equal to F of 200. So we do negative 0.005 times 200 squared plus 2 times 200 plus 5. And if you do all that out, you get 205 feet. So that's the maximum height. And if you wanted to use your calculator to support you, you could just throw that particular function into your calculator. And there's your graph right there. It shows your maximum height, 205 feet at a distance, a horizontal distance of 200 feet. So let's get a little picture of that to capture it. There we go. Kodak moment, yes. Okay, so there's the answer right there. You can also, on your calculator, go to second calc and go down to where it says maximum. If you hit enter, you do a left bound, you just put your cursor somewhere near the maximum value, enter, and then move your cursor somewhere to the right of the maximum value, enter. Every time you see guess, you say enter, and voila, there's your maximum value. Okay. Remember, your maximum value is the output. That's what we're always interested in. Okay. Find the distance the arrow travels before it hits the ground. So to know that, we'd have to know how far it travels from beginning to end. Well, if it goes 200 feet to here, right, till we hit our maximum, how far do you think that arrow is going to travel? 400. We could back that up again by going second calc 0, because that's a 0 of the function, the x-intercept. Let's move. We're just going to guess here. Well, we'll go. I don't want to do it that way. I think we can put in, let's say 300. We know that's to the left of 400. And to the right, I wonder if it will allow us to put something in. Let's see. No, it's invalid because we don't have the domain. All right. I wanted to go to the right of 400. Yeah. Oh, it is? Oh, it is? So I couldn't get my answer by just going 200 this way and 200 that way? I wonder why. Why? My arrow stays at 205 for more than 1 foot. Okay. So I can't use that idea here. So that's why it says find the distance the arrow travels before it hits the ground. 0 equals negative 0.005 x squared. You have to solve this equation for x, which is your quadratic equation. And what did you get for x? 4.402. Yeah. Okay. All right. So I'm still wondering why I can't use the symmetry here. So we have to think about that. Connor? Oh, you just, all right. So I'll leave you that to ponder. What mistake did I make? I know how to use the calculator, but why didn't my idea of just, yeah. Oh, the little bit it's on the ground. So you think it's the length of the arrow. Okay. All right. Let me just set up. We got a minute left, folks. And you know me, I use every minute. And you'll want me to do this for you because you'll have one of these for homework. One of the things, what else has square units? Area. So we want to maximize area. So a farmer has 400 feet of fencing to enclose a rectangular corral. Can you just sit down for a minute, Jonas, so people, all right, you can zone out if you want. To save money in fencing, he intends to use a riverbank for one of the boundaries. So if we call this the length and this the width, it doesn't matter. You have two, I know you've done this so many times, is the area, right? Find the dimensions that would enclose the largest. Well, I don't know how to do this. Do you know how to do this? Well, you know that this equals 400 because this is the, oh, so that's my first mistake right there. That's not A, that's P, that's the perimeter, right? Okay. I need to write my area formula either in terms of W as a function of W or as a function of L. Since I already have one W here, let's write this in terms of W. So solve that. The reason they give you the perimeter is so you can solve one of your dimensions in terms of the other. That's always the purpose. So W equals 400 minus 2L. So now you have your length times your width, right? So I'm actually going to solve this for L because, whoops, L times W. I've rewritten W in terms of L. So my length is my length and my width is 400 minus 2L. So I just substitute the expression for my width in terms of my length. I use my distributive property, and lo and behold, out pops a little baby quadratic expression on the right side. And if you put that in descending order, you can see the value of A and you can see the value of B. So to get your maximum area, you have to find the L value that maximizes the L value of your vertex and then plug it back into your function. So the L value of your vertex is minus B over 2A, which is 100. So when you have a length of 100 feet, you're all set. So you have a couple of choices here. You can put 100 in right up here. 2 times 100 is 200. Subtract it from 400, so your width is 200. Or you can put it right back here and do all this work out if you want. But 100 times 200 is what? 100 times 200? Oh my, 20,000 square feet, right? So when your length is 100, you're going to reach a maximum height of 20,000 square feet. So your maximum area, I'm sorry I had to rush this, folks, is 20,000 square feet. Okay, so this homework's not due until next Wednesday. Have a good weekend. Make sure you put aside a lot of time for studying. And don't forget, you can bring in both sides of one page for notes. But they must be your notes, handwritten notes, okay? Notes that you put together.